In my lab, we looked at lots of different things to try to do this. And one day I was in my office and I got a manuscript to review that proposed to use these magnetoelectric nanoparticles. And this is kind of embarrassing. I was looking at that manuscript and I'm like, that is like not a word. I studied physics at Harvard. There's magnetism and there's electricity and this magnetoelectric, like that, you just made that up. And I'm gonna get you because I'm doing peer review. And as I was going through that manuscript, actually I was wrong. This is like a real material. But it was really interesting because I was like, oh, I haven't heard of this before. Maybe there's something interesting here. The reason why I hadn't heard of it was that it's an incredibly rare material. So most materials either have magnetic polarizability or they have electric polarizability, usually not both. And in fact, there's almost no natural materials that have both of those properties. But the ones that do are called magnetoelectrics. And I want to show you how that works and then why that led to the breakthrough that allowed us to build what I'll show you in a minute. So the way that we create these materials in my lab and now in my company is we take two different materials. One is a magnetostrictive material, so it has the magnetic properties. The other is the piezoelectric material, it has the electric properties. The magnetostrictive material, it vibrates when I turn on an alternating magnetic field. The piezoelectric material, as you're probably more familiar with, creates an electric field when it vibrates. And so if we can combine these two things together, I can apply an alternating magnetic field transferred into mechanical energy, which then creates an alternating voltage. We use magnetic induction for the wireless power mats that you might have at home. We use it for actually every implantable medical device today is recharged using magnetic induction. The way that magnetic induction works is that you have a receiver coil, and we look at the magnetic field lines. Those are the horizontal white lines that I have going this way. A cross-section looks like little dots going through the board. And the magnetic flux is what determines how much energy I get from magnetic induction. That's me counting up every one of those field lines. Magnetoelectrics depends not on the flux, but on the strength. And the strength is the distance between those field lines, right? Now, what's special about magnetoelectrics is that if I make a very, very small device, I've given up all of those field lines. I've given up flux. So magnetic induction is not good. It's really bad at charging things that are small. But magnetoelectrics doesn't care about flux. It only cares about the strength. And so now you see like the strength is the same even though I've made a smaller device. So there's a fundamental difference in terms of the physics of how this scales that allows us now for the first time potentially to make a lot of energy inside of a small device.